Hello, this is Mrs. Myers, and we are going to be doing our lesson 2.3, and it's all about isosceles triangles. First of all, to just remember, isosceles triangle means you have a triangle with two sides congruent, at least two sides, and an equilateral triangle has all three sides congruent. Remember, the word scalene means there's no sides congruent, but right now we're all going to be thinking about isosceles triangles today. So if we have two sides that are congruent, those two sides are called the legs. So we have this leg and this leg are the two sides that are congruent. Where those two sides come together, at this vertex here, that's called the vertex angle. It's always where the two legs come together, two congruent sides. The third side that's not congruent to the other two sides is called the base. And those other two angles are called the base angles. So even if this was, sideways like this, we would have our two legs here, and our base would be this green side here. Our vertex angle would be where the legs come together. So the base doesn't mean bottom. It just has a different definition you got to be aware of. Okay, if you have an isosceles triangle, then if you create a bisector of the vertex angle, okay, so if you're cutting that angle into two congruent angles, then what happens is automatically this bisector going through will be cutting the base in half, also bisecting the base. Not only is it bisecting the base, but it is actually going through that base at a right angle. So this theorem doesn't have a name, but the theorem says if a line bisects the vertex angle of an isosceles triangle, then the line will be the perpendicular bisector of the base. Let's take another one. Here's an isosceles triangle. If I create a bisector of the angle, I'm not focusing on where it's going through the side, I'm just focusing on cutting this angle in half. If I do that, it automatically will cut the opposite side in half, the base in half, and it will go through at 90 degrees. We're going to need that theorem in the proof that we're going to write of this theorem. Now, this theorem is called the isosceles triangle theorem, and that is mainly the theorem that we're working on here. Okay? That theorem says if you have an isosceles triangle, which means the two sides are congruent, then the angles opposite those two sides will also be congruent. You can kind of abbreviate it like this. If the two sides are congruent, then the angles across from those sides will also be congruent. That's a very important proof that we're going to use a lot. A very important theorem that we're going to use a lot, especially in proofs and in solves too. Okay, so if we write the proof of this theorem, okay, so the proof of this theorem is a little bit complicated actually, and it involves an auxiliary line. This time they already drew the auxiliary line for us in the diagram. But if we're given that we have a triangle where xy is congruent to xz, and this drawn-in auxiliary line, xb, is bisecting angle yxz. So bisecting this angle, so we can mark these two angles congruent. That's all given. We're trying to prove that this angle is congruent to this angle. I don't want to actually mark that in my diagram because we haven't proven it yet, but these are the two angles we're trying to prove congruent because we're proving this theorem. If the two sides are congruent, then the two angles across from them are also congruent. Okay, so we're going to start with our given. xy congruent to xz, and xb bisects angle y, x, z. So the first thing you want to do is say that angle 1 is congruent to angle 2 by definition of bisect. And we're going to use this theorem from up here, this one. It's really the whole purpose of that theorem right now is to use it in this proof. XB must be the perpendicular bisector of YZ. So that really comes from both of these. We're going to say XB is the perpendicular bisector of YZ. And it comes from that theorem. And since the theorem didn't have a name, I really need to just state it out. If a line bisects the vertex angle of an isosceles triangle, then it is the perpendicular bisector of the base. Okay, you guys need to kind of not write too big for this proof here. Okay, so that means if it's the perpendicular bisector, I'm going to come off to the side here now. That means that angle YBX and angle ZBX are right angles, right? Because if it's the perpendicular bisector, then those must be right angles. And if they're right angles, then they must be congruent to each other. Angle YBX is congruent to angle ZBX. Remember, that was called the right angles theorem. If two angles are right angles, then they are congruent to each other. Okay, so we have 1 congruent to 2, and we have these two right angles are congruent to each other. Now we want to somehow involve angle Y and angle Z, because those are the ones we're trying to prove congruent to each other. So we're going to have to use the triangle sum theorem here. So since we're going to use an equation where we're adding things together, we want to get the measures of these equal to each other first, by definition of congruent, because we know we're going to have to be substituting in here. Okay, now I'm going to state 2 things about these two triangles. This triangle separate from this triangle. Both of those have the triangle sum theorem that can be applied here. So I'm going to say the measure of angle 1 plus the measure of angle y plus the measure of angle, this one, which we called YBX, equals 180. And I'm going to put it in the same box, actually. The measure of angle 2 plus the measure of angle Z plus the measure of angle, the other one, ZBX, equals 180. I can put them in the same box because they have the same reason. Sometimes we don't want to do that, but that's the triangle sum theorem. Now, I'm going to want to substitute these two into my equations eventually, and this one into my equation. So actually I need to state those measures are equal also, because I have to get those equal before I can substitute them. Oops, definition of congruent. Okay, so since we have, sorry, I know this is very long. Since we have these two things both equal to 180 degrees, we can rewrite them as being equal to each other. Measure of angle 1 plus measure of angle y plus measure of angle ybx equals the measure of angle 2 plus the measure of angle z plus the measure of angle zbx. They equal each other. Now, since the measure of angle 1 equals the measure of angle 2, I can justify subtracting angle 1 from that side and angle 2 from that side. And since ybx equals zbx, I can subtract ybx from this side and zbx from that side. So with all of that subtraction, I end up with the measure of angle y equals the measure of angle z. Subtraction. Which means they're congruent. Which is what I was trying to prove by definition of congruent. Okay, so basically, in a nutshell, right, we were able to say, since these two right angles are congruent and 1 is congruent to 2, then y must be congruent to z because they all add up to 180, and that's the proof. All right, how are we going to apply this? Let's turn the page. Well, if we have an isosceles triangle marked, we know it's isosceles because of the congruence marks, and we're given this vertex angle is 30 degrees, well, if I know that angle D has a value of x, then angle F must also have a value of x because of the isosceles triangle theorem. These two angles have to be congruent. So we would have x plus 30 equals 180, right? So 2x equals 150, and each x has to be 75 degrees. Right? Now, complicated intertwining triangles and everything, we still can apply this isosceles triangle theorem. If we look at this triangle separate from this triangle, right, we want to look at all the clues that they give us here. If we start with the blue triangle, they tell us this is 90 degrees. Well, if that's 90, and these two angles are both the same, they both must be equal to n. Well, if this one's 90, each of these must be 45. Now, if we take the red triangle, this is 50, well then, each of these have to be congruent because this is congruent to this. So if that's 50, that leaves me 130 for these two, right? So 2x plus 50 equals 180, and 2x equals 130. That means x equals 65. So that means this whole angle is 65. The whole thing. But you can see we're looking for m. M is just part of that 65. So if the whole thing is 65, and this little piece we said is 45, then we're going to subtract to get m. It's 20. All right, so you guys try these two, 31 and 32. Try them on your own, and then turn the video back on to check your answer. Okay, so for 31, you should have gotten n is 27. That's just using this isosceles triangle. And then if you use linear pair here, 126, that would be 54. Then you can use triangle sum to get m as 36. For 32, you see all three sides of the triangle marked congruent. Well, if the three angles add up to 180 and all three angles are going to be congruent, then each of them has to be 60. And that's how we get n is 30 and m is 60. Okay, so now the converse of the isosceles triangle theorem says exactly the converse. In other words, if you know the two angles are congruent, then you can conclude that the two sides are congruent. So this is just the converse. If you know the angles are congruent, then you can conclude that the two sides are congruent. So again, this is going to be applied pretty much the same way. Okay, so if we look at this little thing to think about here, if you look at this image, this diagram, they're asking, is WVS congruent to angle S? Well, WVS is here. Is that congruent to S? Yes, because these two sides are congruent, so that would be congruent to this. That's good. Now they're asking, is TR congruent to TS? We'll see what you think about that. This angle is marked the same as this angle, and we just said S is the same. So all three of these angles are congruent. This one, and this one. So in this big triangle, these two angles, base angles, are congruent, so that means yes, the sides across from them would be congruent. So TR is congruent to TS. But then it says, can you conclude that triangle RUV is isosceles? Well, we don't have any way of concluding that because we know nothing about this angle V here. So we can't conclude that that's isosceles. All right, so you guys try 4, 5, 6, and 7. See how you do. Turn the video back on to check your answers. Okay, so these are the answers you should have gotten there. So there's a couple of corollaries. A corollary, we might not have used that word before. A corollary is just like a sub-theorem. It's like if this big theorem is true, then there's these other things that automatically follow, that just automatically are true because of that theorem. And so the first corollary here is if a triangle is equilateral, then the triangle is equiangular. So if you remember, we talked about the smallest angle is across from the smallest side, and the medium angle is across from the medium side, and the largest angle is across from the largest side. Well, if all of the angles are the same, then all of the sides are the same. Also, isosceles triangle theorem, right? If this angle is congruent to that angle, that means these two are the same. And if this angle is congruent to this angle, then that means these two are the same. And so you end up with all three angles and sides the same. So that's the first corollary. The second corollary kind of follows from that. If a triangle is equiangular, then the triangle is equilateral. So it's kind of the converse of the first corollary. If you know all the sides are the same, you can assume all the angles are the same. And if all the angles are the same, you can assume all the sides are the same. But there's something extra I want you to add here. And we sort of used it up above in one of the problems. If a triangle is equilateral, then each angle equals 60 degrees. Right? So that's something to keep in mind. If it's equilateral, that means it's equiangular. That means if they all add up to 180 and they're all the same, each one has to be 60 degrees. It's a really important thing to keep in mind. Okay, so refer to the diagram at the right. What kind of a triangle is triangle ABD? ABD, that's going to be isosceles. What type is BCD? Well, BCD has all three sides marked congruent, so what do we call that? Equilateral. And find the measure of angle ABC. Well, each of these we said is 60 degrees. And this, if this one is 66, then this one has to be 66. And so that's going to leave 48 degrees here. And so the measure of angle ABC, that's this whole angle ABC, is 48 plus the 60, which is 108 degrees. Okay, so big takeaways from today is that isosceles triangle theorem, if you know the sides are the same, then the angles across from them are congruent as well, and vice versa. Okay, thanks.